How did wheeled vehicles become powerful enough to move aircraft, tanks, and even mobile missile systems? And why does that capability quietly shape global military power? A tank sits stranded in the churned mud, its engine silent, blocking the only route forward. The radio crackles with urgency, enemy artillery is zeroing in, and every minute lost puts the entire column at risk. In these moments, the difference between a stalled offensive and a breakthrough hinges on a single machine, the heavy recovery tractor. On the Eastern Front in 1943, German commanders faced this crisis daily. The solution arrived in the form of the SDKFZ-9, a massive half-track built by Famo. At nearly 18 tons empty and powered by a 10.8-liter Maybach 512, it delivered 270 horsepower to a reinforced drivetrain. Its towing capacity reached 28 tons, enough to haul a Panzer IV or, when working in teams, to recover a crippled Panther or even the dreaded Tiger. The SDKFZ-9's secret was more than raw power. Its torsion bar suspension and wide tracks spread weight across the ground, holding pressure at just 8.8 pounds per square inch, barely more than a man's footprint. This allowed it to pull heavy loads across mud, snow, or broken roads where lighter trucks would bog down instantly. Unit logs describe recovery crews winching disabled armor under fire, anchoring the Famo's rear spade deep into the earth to resist the strain. With a 290-liter fuel tank, the tractor could cover 260 kilometers on roads or 100 kilometers cross-country, keeping pace with advancing divisions. In the chaos of battle, these numbers were more than engineering trivia. They were the difference between abandoned steel and restored combat power, between holding a line and watching it collapse. A heavy recovery tractor's true advantage lies in the numbers hidden beneath its armor. The SDKFZ-9's Maybach V12 delivered 270 horsepower, but the real work happened in the gearbox and winch. With a 4-speed transmission and low-range gearing, engine torque was multiplied until the tractor could generate pulling forces up to 40 kilonewtons on the winch cable, enough to drag 28 tons of dead weight, or more when several tractors worked together. Recovery crews would anchor the spade deep, engage the winch, and let the gearing do the rest. Each turn of the drum translated engine effort into slow, relentless movement, overcoming mud, gravity, and the resistance of a wrecked tank. Gearing was only part of the equation. Every kilometer burned fuel at a rate that set hard limits on operational fuel and range. The SDKFZ-9 carried 290 liters of fuel, enough for 260 kilometers on roads, but only about 100 across rough country. Every recovery mission had to be calculated. Too far from supply lines, the tractor itself could become the next stranded asset. Logs from the Eastern Front show that fuel shortages and mechanical strain often forced crews to abandon even the most advanced vehicles if recovery could not be completed quickly. The math set the boundaries for what was possible. Gear ratios and winch pulls defined what could be moved, while fuel capacity and range dictated how far. These constraints would only grow more severe as the scale of military hardware increased after 1945, demanding new engineering answers for even heavier loads and longer distances. The leap from battlefield recovery to towing bombers and mobile missile systems begins with a simple calculation. How do you keep a 90-ton weapon from sinking into mud or snapping a bridge? The answer lies in how weight is split across axles and how power is delivered to each wheel. Cold War engineers faced a new scale of problem. A transporter moving an 80-ton missile or a 60-ton main battle tank could not rely on brute force alone. Instead, they multiplied the number of axles, 8, 10, even 16, so that each carried only a fraction of the total mass. On the Soviet MZKT 79221, a 120-ton missile launcher is spread over 10 axles, holding the per-axle load to just 6.5 tons. This keeps ground pressure at about 7 pounds per square inch, roughly the same as a human footprint, and far less than a standard truck. The math is unforgiving. Ground pressure is calculated by dividing total vehicle weight by the combined contact area of all tires. On a 70-ton transporter with 8 wheels, each tire must support less than 9 tons. Widen the tires, add more axles, and the pressure drops. This is what lets a 100-ton load cross soft ground, snow, or sand without bogging down or tearing up roads. But the axle count is only half the equation. Each axle must receive torque, the twisting force that turns wheels and starts movement. High-displacement diesel engines, often 12 to 16 liters, are paired with gearboxes that multiply torque at low speeds. The result? A modern heavy transporter can deliver over 50,000 Newton-meters of torque per axle, enough to get a 90-ton missile system rolling from a dead stop. Every design choice, from axle layout to tire width and engine gearing, is a direct response to the challenge of moving extreme weight without losing mobility. These numbers set the stage for the next leap, not just in engineering, but in military doctrine itself. On a Soviet airbase in the 1970s, a transporter erector launcher idles beside a missile silo, its engine rumbling deep. The technical leap is not in what it carries, but in the force it can unleash at the wheels. Over 90,000 Newton-meters of torque, multiplied through gearboxes and planetary hubs, enough to move a 120-ton missile system from standstill across open ground. This number is not just a feat of engineering, it is a direct answer to a strategic problem: how to keep nuclear forces mobile and survivable under the threat of a first strike. During the Cold War, intelligence analysts in both NATO and the Warsaw Pact tracked not only missile counts, but the capabilities of the vehicles that could relocate them. Internal memos from logistics planners, declassified decades later, reveal the calculation at the heart of deterrence. Each mobile launcher required at least 48 hours of continuous reconnaissance, confirmation, and targeting before it could be engaged. This targeting delay, made possible by the ability to move 90-ton loads off-road and out of sight, extended the window for retaliation and forced adversaries to reconsider the feasibility of a preemptive attack. The math behind these vehicles is precise. A 1,500 horsepower diesel, peaking at 4,500 Newton-meters, sends its force through a 20-to-1 final drive. At the wheels, torque exceeds 90,000 Newton-meters, enough to overcome mud, snow, or soft ground and keep a missile on the move. The doctrine is clear: mobility buys time, and time equals survivability. In the words of a Soviet logistics officer, as long as the transporter moves, the missile survives. This is where engineering meets geopolitics. The technical capacity to tow extreme loads became a central pillar of nuclear strategy, shifting the balance of power from fixed silos to road-mobile launchers. The challenge now moves to a new arena: how to make these platforms interoperable across alliances, and how to maintain the same survivability in a world where rapid deployment and distributed operations define deterrence. Moving a 100-ton missile module or main battle tank across NATO is not just about horsepower, it is about meeting strict alliance standards. STANAG 2322 sets a hard limit: no more than 10 tons per axle, whether rolling through Polish forests or over Belgian bridges. This number reflects years of engineering, weighing the demands of heavy payloads against the realities of roads, bridges, and transport aircraft. Vehicles like the Rheinmetall MAN HX and Oshkosh HIM TT are built for this challenge. The HX-81 8x8, for example, can tow over 100 tons while keeping each axle under 10 tons. The key is in the design. Multiple axles, wide tires, and active suspension all work together to spread the load. Modular ISO container couplings and NATO standard quick connects turn a single chassis into a flexible platform, ready to haul a missile one day and a radar shelter the next. These standards transform national assets into alliance assets, making rapid redeployment possible across thousands of kilometers without special permits or delays. 54,000 Newton meters of torque at the wheel, this is what the Rheinmetall MAN HX heavy transporter delivers. It is not just a number, it is the force needed to move a 100-ton load from a standstill, even through mud. The HX achieves this with a 2,300 Newton-meter engine, multiplied by a 20-to-1 reduction across the transmission, the transfer case, and portal axles. British Army field trials with Challenger 2 tanks saw sustained torque above 52,000 Newton-meters per driven axle. 8-wheel drive locks in, spreading weight so no tire carries more than 10 tons, keeping ground pressure low enough for soft ground. But power means little without range. The HX's 1,500-liter fuel tank and tuned diesel curves support 36 hours of operation at 40 liters per hour, enough for 1,000 kilometers of towing without refueling. Danish Army exercises in 2022 confirmed this. 1,480 liters used over 38 hours with no breakdowns. Extreme torque and fuel autonomy combine to make the HX the platform that moves strategic assets anywhere, under its own power without waiting for supply lines. Right now, every credible deterrent on Earth still relies on logistics muscle measured in thousands of horsepower and hundreds of tons. As doctrines evolve, the contest is not just firepower, it is mobility. The world's balance of power still rides on wheels. If you value these hidden truths, join the search below.